Uh, Good morning, everyone. Those of you at the back, can you hear me clearly? Okay, so I want to welcome you to another multivariate statistics class. Today, we got two materials that I'm actually going to walk you through. I'm going to walk you through material on correlation matrix and, of course, miscellaneous. Okay, so if you look at what we started uh, on Friday, okay, I introduced you to this outline. We've already achieved data matrix. We've done covariance matrix. We are left with uh, number 3 and 4, and of course, that will be our focus today. And I also want to make an announcement about the president of the university has asked the members of the university community to observe a minute silence at exactly 9:30. This is 9:06. So by 9:30, I'm actually going to remind us to observe a minute silence in honor of Alice. So I just letting you know that. Okay, so I've already published all my recordings. You can check my YouTube channel. Okay, so I make sure it is 5041 spring 2026. Okay. Okay, so let's go into the uh reason why we're here. Um, you know, why do we need a correlation matrix? Um, I'm actually going to have a recall, a recap on what we did on Friday, because we don't just do what we do. There's a reason why we do what we do. So the whole thing is going to start from us collecting data. If we actually want to get certain information, if you want to take a decision that we don't want to regret, we need to collect data. And of course, at times, when data are collected, they are collected over so many variables, okay, and across observations. And we're actually going to call that a multivariate data set. And of course, when I have multivariate data set, uh, it's actually uh, going to be in form of a matrix. The fact that the data set are presented in rows and columns, qualify to be a matrix. So, and when we have it in matrix form, we have it in matrix form for easy analysis, okay? Because we're actually going to benefit from idea of matrix algebra in dealing with multivariate data set. Now, if I want to look into, if I want to measure relationship among variables, uh, I'm actually going to start by getting what I call covariance. Okay, the covariance measure how variable varies together. Okay, if I really want to know the relationship or they have, but uh, we got a limitation with covariance matrix because of the fact that you know, when you are working with variable, for instance, if you are working with age, maybe you have age in days, if you change the unit, probably to weeks or to days, of course, I mean to years or weeks, okay, if you decide to change a unit of a variable, of course, you expect the value of the covariance to change. Covariance, because of that, covariance is not consistent when it comes to measures of relationship among variables. And that is why we need correlation. Okay. So, which means in order to overcome the limitation of covariance, inconsistency in covariance, we need to standardize covariance. And I'm going to say this. Correlation is a standardized covariance. When you standardize it, of course, you know, even when you change the units, okay, of your variable, okay, it's actually the value of a correlation will stay the same, okay, and that is the reason why we use if I want to look into the strength of the relationship between variable, if I want to investigate or whether it is weak or it is strong, okay, then I'm actually going to use correlation instead of covariance. You know, the covariance is only going to tell me where the way they vary together and the direction of the relationship. The covariance cannot tell us the magnitude of the relationship, the strength of the relationship. And what is going to tell us, what is going to give us that information is correlation. Okay, does that make sense? Okay, now the same way we have covariance matrix, we're also going to have correlation matrix, and there's something I need you to pay attention to. In the diagonal of a correlation matrix, it's always going to be one. I just want you to take note of that. Always going to be one. Okay, if you take a look at uh if you take a look at the diagonal, you can say 111. That very 111 implies you know, correlation between the same variable, you know, the two variables that are the same, okay? Correlation between weight and weight. I expect weight and weight to be perfectly correlating with itself. And that's why you're going to have 1, 1, 1, 1 in the diagonal of a correlation matrix. Okay. In the half diagonal, okay, in the half diagonal, that's where you're going to have a correlation between pairs of variables. Does that make sense? Okay, so that is that. And well, if you take a look at the notation, an uppercase R, okay, that's what we use to denote, you know, a correlation matrix. And if you are wondering about how do we obtain each of the elements within the correlation structure, okay, this is the formula that we use. Okay, if you take a look at this formula, the numerator here is the covariance. The denominator is a product of the standard deviation. For instance, if I'm talking about two variables, J and K, okay? If I'm talking about two variables, J and K, and I want to figure out, okay, the correlation between variable J and K, okay, I may be talking about correlation between weight and height. A doctor may be interested in that. Okay, so the correlation between weight and height, okay, the numerator is going to talk about what is the covariance, what is the covariation between the two variables under investigation, divided by the product of the standard deviation of variable J and variable K. Okay, so this is the formula here. Okay, now you're going to make use of this formula if you actually want to get that in a scalar form. Okay, but if you want to get that in a matrix form, please I need you to pay attention. I remember when I was walking you through uh you know, the covariance on Friday. In a matrix form for covariance. I remember I said I used S equal 1 over N, okay? And I remember I said SC, okay, transpose SC, okay? But I needed to see something now. In that of the uh correlation, it is not SC, it's SS. Then I want to differentiate between the two. The SC that I mentioned on Friday is actually centered matrix S. You know, the way you centered, you know, when you have a data matrix S, you want to get a covariance, you need to center that. And the centering that is, you know, subtracting the mean, or, you know, the mean of a variable in a particular column, you know, from each and every values in the column. You know, that is how we figure out the covariance. But you know what? If you want to obtain the you want to obtain this guy S S S subscript S. That is a standardized. That S means this particular S here means standardize. How do I standardize data matrix? Or to be able to standardize data matrix, what I'm going to do, I will for centered. What am I going to do in centering? Well, wait a minute. I think this is not showing. I'm gonna do this right now to make it show. 1 second. Okay, so I just showed it right now. S. Uh, 1 second. Okay. I'm gonna stop my share. I want to see why it's not showing. I'm trying to write something, but okay, this is showing now. Let me let me also see this. Oh, okay. Maybe I should go back and do some cleanup. Before I go back, maybe I wrote something at the beginning. Let me go to on page one. Okay. Let me see this. Okay. Uh, yes. Okay, it's showing now. Okay. I think I'm gonna stop sharing. I'm gonna share that again. Okay, I'm also want to say this. So if you know you don't feel safe attending lecture in person, you can join my Zoom. Where I got a lot of students on my Zoom right now. So I'm flexible. 1 second. I'm gonna reshare this. And let me see if it's gonna show. Okay, it's showing right now. Okay, so I'm gonna have a recap on that. I remember on Friday when I want to obtain the covariance, I actually we use this guy here. Please, like I said, pay attention to notation. Now you can see I got we have 1 over for covariance 1 over n. The transpose of SC, that very C represent centering. So which means subtracting. When I have my data matrix, I'm actually going to subtract the mean of a particular column from every value in that column. Okay, that is centering. And when I do the centering, I find the transpose and multiply by the SC, then I divide by N, then I'm going to have covariance. But if I want to get, how am I going to get the correlation? On the other hand, okay, take a look at this guy now, okay? If you take a look at the correlation, instead of SC, it is SS. And what is the meaning of the SS that I'm actually talking about, okay, is standardizing, okay? And how do I standardize? Okay, when I divide what I've centered by standard deviation, then I'm standardizing. So if you take a look at this, okay, take a look at each of that, okay? After subtracting mean, after subtracting mean from each and every value in the column, I divide by the standard deviation. There's something I need you to pay attention to. Take a look at this. All of this for one column, which means I know the mean of that variable. That variable may be height. I have the mean for the height, and I'm subtracting that mean from each and every variable, every value in the height, then I divided by the standard deviation. Okay, so when I do that, then I have a standardized X. This is a standardized data matrix. Okay, that's a standardized one. So if I have a standardized, what I'm actually going to do, I will find the transpose. Okay, well, what do we mean by finding the transpose? Is changing the element in the rows to column, or changing the column to row, then I'm going to multiply by the original one, and I divide by n, and that will give me correlation. Okay, and I'm just trying to explain how to obtain the correlation matrix using the knowledge of matrix algebra and the covariance matrix. Okay, and of course, I think I walk you through that formula the other time. Okay, if I want to find uh, the correlation between two variables, okay, in a scalar form, each element, if you don't want to go by way of a matrix, you can actually use that formula. And of course, we can use that formula provided the variance of each variable is greater than zero. But don't forget uh, what I have here. Okay, what I have at the denominator is the square root of the variance. We expect the variance to be greater than zero, because when variance is equal to zero, the denominator of this fraction will be zero. And you know the mathematical implication, right? When the denominator of a fraction is zero, it will be undefined. Okay? And that's why here we are emphasizing that the variance of each variable has to be greater than zero. Otherwise, we will not be able to obtain correlation. Okay, so we got a lot of properties. And let me tell you this situation where the two variables are equal and you're trying to find the correlation, it should be 1. Correlation equal to 1 indicates a perfect positive correlation. And that is why when you take a look at the diagonal elements of the correlation matrix, they're all going to stay 1, 1, 1, 1, 1, because that gives correlation between a particular, a variable and itself. Okay, so a variable should be perfectly correlating with itself. Okay, then another thing I wanted to know is this: the trace of R. When I say trace of R, what do I mean? I'm talking about adding the values in the diagonal together. The trace of R is addition of 1, 1, 1, 1. The trace of a correlation becomes the number of variables. That's what I'm trying to say here. That's what I'm trying to say here. Please pay attention. That's what I mean. Here, I mean the trace of R equal P. What is P? P is the number of variables that we have. If I had 1, 1, 1, 1, 1 all together in a matrix, in a correlation matrix, that should give me the number of variables under investigation. That's what I mean. That's what trace means. Okay, and I also want to say this. By the time we start principal component analysis, where we have what we consider what we call the eigenvectors. Okay, the lambda 1, the lambda j, the sum of that will also be equal to the p. Okay, I'm going to remind you by the time we start. And another thing I wanted to take notes. Okay, we have condition under which lambda j can be 0, and condition under which lambda j can be greater than 0. Let me tell you this. The lambda in principal component analysis, they represent the variances. I'm going to say that again. The variance of a particular principal component is actually the lambda. Okay, by the time we get to that topic, I'm actually going to give explanation. So when variance equal to 0, variance can be equal to 0 in a situation where the number of observation is less than the numbers of variables. That we occur in high-dimensional data. High-dimensional data, when the number of variables, numbers of features is more than the number of observations, we expect the variance. We expect the lambda j to be equal to 0. We have a way to deal with that. Don't be scared, okay? We have a way to deal with that. Okay. Okay, so when lambda j is greater than 0, then we're actually going to say, x are linearly independent. Let me tell you, linearly independent it's actually required if I want my matrix to have a full rank. I'm going to tell you the implication of matrix having a full rank as time goes on. Okay, now we're moving. I think I remember on Friday, I talked about this Cauchy squash inequality. Okay, uh, according to Cauchy and squash, if I square covariance, okay, uh, the square of covariance is less or equal to the product of the variances. If I have two variables, J and K, their variance exists. Okay, the square of the covariance is less or equal to that. So if it is less or equal to that, if I divide both sides by the products of the square of the variances, I'm actually going to have this. And you know what? Uh, if this is less or equal to 1, then it means that this guy here, because the correlation that I walked you through the other time, RJK is actually the covariance, okay, SJK, okay, divided by the standard deviation of variable J and standard deviation of variable K, okay. Now, if you take a look at what is happening here, it's like squaring this. When you square all of this, when you square that, this is the correlation also going to be squared. That's why you see R squared JK less or equal to 1. Okay. When you square a correlation in statistics, that is no longer a correlation. Can somebody remind me what we call that in statistical analysis? When you square correlation value, it is no longer called a correlation. Can somebody remind me what is called? What is being called? Has anybody heard about coefficient of determination that we call R squared? Okay, we're still going to talk about that. If I want to know how good is my model, then we make use of R squared. Okay, it's used for goodness of fit of a model. Okay, we're going to talk about that. Okay, as time goes on. Okay, now how do we do it in R? Now, let me tell you this. You know, I'm only showing you this behind, the theoretical proposition, just for you to be able to know what happened behind the scene. Okay. Now, because you may want to question why, if I put something into a software and you get a result, the result are not just, it's not just coming out like that. There's a formula that we program, behind the scene. If the formula is wrong, then we expect the result from software to be wrong. That's why I need to first show you, okay, the theoretical formulation aspect of that, before we go into how do we do it in R. Okay, now, if I want to do it in R using software, okay, this is how we do it in R. We have easy way to do it. We have hard way to do it. The hard way to do it is when you code the formula. Look at that. I'm coding the formula here. Okay, there's another way to do it. Okay, but you know what? The most easiest way to do it, because I don't want to waste my time. Look at oh my God, look at that. If I have a matrix X already defined, if I want to get a correlation matrix, I'm just going to write COR into X. And it's going to give me correlation matrix. Just COR. For the covariance, and that will be COV. Okay. Okay. At this point, um, I um, I'm gonna we're gonna stop for a moment, and I want to use this opportunity as directed by the president of the university. We want to have a minute of silence, and when we're having it, I just want us to breathe. I want us to actually stay calm and having sober reflection. So when it is time for you to do it, I'm gonna tell you. This is 929. Okay. So okay, let's start. May the soul of the departed soul rest in perfect peace. Uh, I want to use this opportunity, uh, just like what my children normally ask me, why can't we be happy all the time? I don't know why. But there's something I believe, even though I know there's a lot of variations in the world, a lot of uncertainty. In fact, the world we live in right now, there's uncertainty within uncertainty. But no matter what, I want us to exercise calm and use this opportunity uh, to get connected with your loved ones. Uh, be mindful of one another. I my experience in the world has showed me nobody can live in isolation. I mean, we need one another. Okay, so make sure you reach out. If there's anyone who actually maybe you need resources, university resources are available. Okay, so because we I don't want a situation whereby um you're not gonna be in the right frame of mind. So no matter what, we have to be strong and you'll be happy. Okay? Okay. Uh let's come back to business. So we have easy way to do it in R. We have a hard way to do this in R. Um, here, this is actually saying the the dimension of my correlation is 11 by 11. Let me say this. Covariance and correlation matrix, they are always a square matrix. I'm going to say that again. Covariance and correlation matrix, they are always square matrix. When I say square matrix, the numbers of rows and the numbers of columns are always going to be the same. Okay? But you can if you are the, if you it depends. If you are not interested in the whole data set, if you take a look at the one I did here, where here I'm trying to specify that I want a correlation, 1 to 3, 1 to 6. Like here now, this is not a square one, but if you're using the whole data set, okay, and you want to obtain a correlation on the data S, of course, the number of rows and the numbers of columns have to be the same. Okay, this is going to be the end of the first material. Is there any question before I go into miscellaneous topics? You're good, right? Okay. Now I'm gonna stop my share. Then I'm gonna share the next material. Like I said, if you need clarification, make sure you ask me question. You pay for the service. Okay? Oh, 1 second.